Okay, now that we have learned the fundamentals of how to apply nodal and mesh analysis, let us start looking at some advanced circuit theorems. And these circuit theorems are all based on the concept of linearity. Now, we're going to discuss linearity, and then we're going to talk about a technique that arises from linearity called superposition. So, let's first begin. What is linearity? Well, all the circuits we're going to study in this class, in circuits 1, all of these are going to be linear circuits. And a system is linear by definition if it meets this following definition, which you have probably seen before in your math courses. A system is linear if it meets the following definition. Given a system, and this system can be anything. In this course, it's going to be a circuit, but it can be a mechanical or a biological system. So, given any system which is defined by y is equal to f of x, some system y. And let's assume we have two inputs. So let's assume that x is either equal to x1 or x2, two possible inputs to that system. So given this, the system is linear if and only if the following is true. F of C1x1 plus C2x2 is equal to C1 times fx1 plus C2 times fx2, where C1 and C2 are arbitrary constants. So that is the classical mathematical definition for linearity. And once again, this is probably almost certainly something you've seen before in math courses. Well, it turns out that in this class, in circuits 1, all the circuits we're going to study will be linear. So we're going to make it easy. We're only going to study linear circuits in this course. However, in the real world, circuits are generally nonlinear. And when I mean real world, what I mean is transistor and diode circuits. Which means that linear circuit theorems are no good in a nonlinear system, which would kind of perhaps lead to a rather obvious question. If most real-world circuits are nonlinear, why are we learning this material? Because as it turns out, even with a nonlinear circuit, you can approximate it as a linear circuit in special cases, and then you can use all the techniques in this course to study it. So it does turn out that nodal and mesh analysis and all these other techniques are in fact extremely useful if you can do that linear approximation, which is exactly what we learned to do with transistor and diode circuits. Okay, so given this definition of linearity, there are several advanced circuit theorems we can apply with it, that basically build upon the nodal and mesh analysis techniques, but gives us some additional tools that we can use to analyze how circuits behave. So let's talk about the first one. And the first one is superposition, which applies to all linear systems, including linear circuits. So a linear circuit obeys the principle of superposition. And what is superposition? Well, what it says is this. When a linear circuit is driven by more than one independent source, and this is the important part, independent source. So when a linear circuit is driven by more than one independent source, in other words, it contains more than one independent source which is either supplying or absorbing energy. The voltages and currents in the circuit are the sums of the partial currents and voltages due to each independent source acting alone. When a linear circuit is driven by more than one independent source, the voltages and currents in the circuit are the sums of the partial voltages and currents due to each independent source acting alone. A bit of a mouthful. What does it mean? Well, the easiest way to illustrate what this means is to work an example and to go through the procedure. Let's draw a circuit, and let's solve it using the technique of superposition. So I have two independent sources, a 120 volt source and a 12 amp source in this circuit. I've got the following resistors, 6 ohms, 3 ohms, 2 ohms, and 4 ohms. And let's define some currents. I1, I2, I3, and I4. What I want to do is I want to find those currents by superposition. So you look at that and say, well, Dr. Holman, can't I go ahead and solve and find those currents right now? Absolutely. If I ask you to find I1 through I4, you can use nodal or mesh analysis and work this problem right now yourself. But we're going to do this with superposition, which is going to tell us something else. It will tell us what the contributions of these four currents are due to the 120 volt source acting on the circuit, and then due to the 12 amp source acting on the circuit. So that's what superposition tells us. It's not a way that we normally use to solve every circuit, but it will tell us what the different sources are contributing to these various currents. So let's go ahead and do that. So let's talk about our procedure. How do we apply superposition? Step one, for a circuit with n independent sources. What we're going to do is we are going to set all independent sources but one to 0. So we're going to analyze our circuit with one independent source at a time. Any other independent source in the circuit gets set to 0. So in this case, I have two independent sources, which means I'm going to go through this procedure twice. So I'm going to set all the sources but one of them to 0. Or what I'm going to do is I'm going to deactivate all sources but one. So it doesn't matter which one. Just pick one source, keep that one, and deactivate the others, or zero them out. How do you zero out a source? Well, if I've got a voltage source and I set it to 0, I deactivate it, what does a 0 volt voltage source become? Well, the voltage here and the voltage here, these two node voltages are the same. So there's no voltage difference across it, but the current can be anything I want. So what do you have when you have a voltage source with 0 volts? Well, it turns out a voltage source with 0 volts is no different than a wire. A 0 volt voltage source is just a wire. It has 0 volts across it, and any current can flow through it you want. So a zeroed source becomes a wire, a short circuit. What about a current source? What if I set a current source to 0? Well, in this case, clearly the current is 0 between these 2 points. But at the same time, the voltage across that current source can be anything. So I've got a current source with no current flowing through it and no restriction on the potential of those 2 nodes. What does that become? Well, it turns out that a 0 amp current source is no different than an open circuit. So 0 to voltage sources become wires. 0 to current sources become open circuits. So you have to remember this, and this incidentally is a very common error that students will make. They will sometimes short out a current source instead of opening it up and turning it into an open circuit when they apply superposition. All right? So you zeroed out. What's the next step? The next step is we're going to calculate any desired partial voltage or current due to the one remaining independent source. So all of our sources get zeroed out but one. And now we solve and calculate the partial voltages and or currents due to that single remaining source. Next step, we now go through and repeat 1 and 2 with each of the n minus 1 remaining sources. So we're going to repeat steps 1 and 2 n times, because n is the number of independent sources we had in the circuit. So I have to solve n partial circuits given n independent sources. So in this case, I have 2 independent sources. I'll need to solve 2 partial circuits. All right? Step 4 is once I do that, I can now go through and I can add together the currents or voltages, the partial voltages and currents, due to the n different sources. So add the n different partial currents or voltages together. The sums of those partial currents and voltages will equal the voltages or currents from the original circuit if all of the sources were present. So the sums of the partial voltages or currents you get from each of these steps, if you add them together, will equal the voltages or currents with all of the sources activated. So if I go through and apply superposition correctly, I'll get 2 partial sets of currents for I1 through I4. And then when I add those together, I should get the same I1 through I4 that I would get if I just solved the original circuit. That's what superposition says. In effect, it's saying the total is equal to the sum of the parts. Pretty straightforward principle. Only in this case, we get some insight into how much each of these currents, how much of that is due to the effect of this source and how much is it due to the effect of that source. So that's how we solve. Now, one thing I want to add, and we'll do an example of this a little bit later, is there's one final step. What if you have a dependent source? Dependent sources are not activated. You treat a dependent source like a resistor. It will be in every circuit. So dependent sources, we just treat them like resistors. They will appear in every circuit. We do not zero them out. We do not try to solve independently for a dependent source. Okay? So let's go through and let's work this problem. Let's use this technique, and then let's solve for these partial currents. All right? Okay, so let's begin by keeping the 120 volt source, and let's zero out the 12 amp source. So let's calculate, let's do a partial circuit due to the 120 volts. So I'm going to do that one first. Therefore, I'm going to zero out the 12 amp source. This becomes 0 amps, which means this just becomes a wire, an open circuit. Okay, now I'm going to calculate the partial currents, and I'm going to annotate these. I'm going to call this I1 prime, I2 prime, I3 prime, I4 prime. So this indicates the partial currents due to the 120 volt source. So now that I'm here, I can apply any technique I want to solve this. Let's do it nodally. I like nodal analysis, and there's a voltage source in it, which means this is going to be 120 volts. And I'm going to call this V1. That is my only undefined essential node. And in this case, once again, I'm going to draw my voltage drops across those resistors. I'm just sticking with the directions of the currents that are already there. No point in defining them differently. And in this case, what I get is, for my V1 node, I get that 120 minus V1 over 6 must be equal to V1 over 3 plus, I can add these two resistors together, V1 over 2 plus 4. And if I solve this, one equation, one unknown, what I'll get is that V1 is equal to 30 volts. And in this case, now that I've done that, once I have that node voltage, the currents are easily calculated. So now in this case, what I've got is that I1 prime is therefore equal to 120 minus 30 over 6, and that'll be equal to 15 amps. I2 prime will be equal to, in this case, 30 over 3, which will be equal to 10 amps. And I3 and I4 in this partial circuit are clearly just the same current. So I3 and I4 are both going to be equal to 30 over 2 plus 4, 6 is equal to 5 amps. So here are my partial currents due to the 120 volt source. All right. Now let's do the partial circuit with the 12 amp source. So I'm going to put my 12 amp source back. And now I'm going to zero out the 120 volt source. And once I do that, this becomes 0 volts. That means this node is 0 volts, and in other words, this is just a wire. This just becomes a wire. This is all just now the ground node, along the side and along the bottom. Okay? So now I need my partial circuit due to the 12 amp source. And once again, I'm just going to use nodal analysis. I'm going to stick with that. In this case, I'm going to find I1 double prime, I2 double prime, I3 double prime, I4 double prime. And now let's go through and solve this. I'm going to give this a different variable name. Let's call this V2 and V3 to distinguish from the V1 I had in the other circuit. All right. So in this case, once again, I'm just going to stick with the same currents, the same voltage drops. Makes it easy. So for the V2 node, what I'm going to have is 0 minus V2 over 6 is equal to V2 over 3 plus V2 minus V3 over 2. For V3, I've got V2 minus V3 over 2 is equal to 4, pardon me, V3 over 4, excuse me, plus 12 amps. Once again, 2 equations, 2 unknowns, and if I solve, what I'm going to get is that, in this case, V2 is equal to minus 12 volts, and V3 is equal to minus 24 volts. So once I have those nodal values, those node voltages, I can now go through and calculate the currents. So in this case, I1 double prime will be equal to 2 amps. I2 double prime will be equal to minus 4 amps. I3 double prime is equal to 6 amps. And I4 double prime is equal to minus 6 amps. So once again, I'm just applying Ohm's law just as I did before to get these values. So these partial current values are due to the 12 amp source. All right. Now, what are I1, I2, I3, and I4? What are those original currents? Now I just go through and I add together the partial currents. So in this case, I1 is equal to I1 prime plus I1 double prime will be equal to 17 amps. I2 is equal to I2 prime plus I2 double prime is equal to 6 amps. I3 is equal to I3 prime plus I3 double prime is equal to 11 amps. And I4 is equal to I4 prime plus I4 double prime is equal to minus 1 amp. And that is my answer. So here are the four currents. I've simply summed together the partial currents due to the two independent sources. Now, I want to emphasize something. If I went back to the original circuit, I could find I1 through I4 just by solving that original circuit. I didn't need superposition to find those four currents. But what did superposition tell me? It told me how much each of those sources contributed to those four currents. So if that's a piece of information you need to know, then you want to use superposition. But in general, if you're just given a problem and you're just asked, find this voltage or find this current, you don't need to use superposition. And I mention this because more than once on an exam, I've had students who decided to apply superposition when the problem didn't ask for it. It didn't ask them to figure out or to decide what the partial value of some voltage or current was. And so instead, they spent a lot of time working a problem and making it more difficult than it needed to be. So if you have to find out the partial value, you want to use superposition. And as we're going to see later on, there are other kinds of analysis techniques or cases where superposition is very useful. But in general, superposition is not something you're going to use all the time. It's a very useful hammer, but that doesn't mean that everything is a nail. So use superposition wisely, and in general, it will be very obvious when you want to apply it. Otherwise, it's not something you need. But it does simply illustrate that given any system with multiple inputs, the responses in that system are simply the sum of the individual inputs, or simply due to the sum. The partial value is due to the sums of those individual inputs. And that's in a nutshell what superposition is. And it applies to linear circuits. It applies to linear systems of all types. Okay? So next time we'll work another example of superposition, only this time we'll include a dependent source just to show how we deal with dependent sources. And as I said before, as we're going to see, we leave them alone. They're going to be in every partial circuit. So we'll do that next time.